Good evening, Hereford. A pleasure to be here. A pleasure to be here live rather than virtually. So yes, this talk it's not rocket science, and you can see perhaps from the subtitle, well, yes, I am talking about rocket science, but really rocket science isn't hard, despite the fact that everybody uses that phrase. It's not rocket science as if it can't be that hard. Rocket science isn't hard as long as you skip the maths. And that's what I'm going to try and do. Put the maths to one side and convince you that anybody can understand rocket science. Just put the maths to one side and think about the ideas, the concepts.
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science.
Yes, and I'm not talking about rocket technology. I'm not talking about how you get a Saturn V to lift off the Earth's surface. I'm not talking about how you get it to lift 100 tons into Earth orbit. Rockets are easy. You just put fuel in the engine, the exhaust comes out one end, and by the conservation of momentum, the rocket goes up. So that's easy stuff. Rockets are easy. Okay, took a little bit of engineering to build a Saturn V rocket, but okay, we can understand how that's done. What I'm talking about is basically what rockets do in terms of how we get a spacecraft from somewhere in the solar system to somewhere else in the solar system. So I'm not thinking about rocket technology, I'm thinking more about orbital mechanics, how things move under gravity and how we get spacecraft to explore our solar system. How we get from A to B, I'll be looking at how we get to Mars, and then thinking about how we get to other parts of the solar system, in particular the outer planets, for instance. And the latter part of the talk is trying to explain, without any maths, what Lagrange points are all about. How is it that we can park a spacecraft out there in the middle of nowhere, 1 million miles away from Earth, and it apparently just sits there quite happily? What are these parking places, and why do they work? So firstly, what do rockets do? The basic idea of rocket science. If you ask not necessarily a group of astronomers, but if you ask a man in the street, what do rockets actually do? What's their primary function? You will often get the answer, well, a rocket's prime purpose is to lift things up above the atmosphere. Well, yes and no, that's not actually their primary purpose. If you think about it, the space station and the Hubble Space Telescope, for instance, are still inside the Earth's atmosphere. They're only a few hundred kilometers above the surface. It's rather thin up there, the air, but it's still actually inside the Earth's atmosphere. The prime reason for a rocket to get things into orbit is to give these things horizontal velocity. The vertical direction doesn't actually matter. Okay, it helps to get above the atmosphere so you don't have the air resistance of stopping objects orbiting the Earth. So yes, it's a good idea to get above the atmosphere, but it's not essential to go into orbit. If you want to go into orbit, what is essential is horizontal velocity. It's nothing to do with vertical velocity. We've known that for more than 300 years. Newton had it in his Principia from, what date was that? 1686. So for nearly 350 years, we've known that it's the horizontal velocity that matters. The thought experiment was, what if you place a cannon on top of a mountain, fire the cannonball sideways? If you don't fire it very fast, it'll drop back to Earth, indicated by paths A and B. If you fire it fast enough, it'll go all the way around the Earth, as indicated by path C. So the need for horizontal velocity, this has been appreciated for an awful long time. So yes, initially it goes up vertically. This is how we always think of rockets. But notice that it's not too long before the rocket starts to tilt over. This isn't an accident of the way the cameras are photographing the rocket. It is genuinely tilting over because before long, this rocket's job is to make sure that horizontal velocity starts building up. It needs a little bit of height to make sure it's well above the launch pad, etc., but it's only a matter of seconds, if not minutes, before it starts to lean over, and then it starts to build up its horizontal velocity to give you the speed necessary to go into orbit. If you didn't do that, if you simply had a rocket that does just go up vertically, what happens when you switch the rocket off? It comes back down vertically, and that's exactly what Blue Origin was all about. You basically have a small rocket and a small group of individuals who are prepared to pay good money, and you send them up, and they might reach an altitude of 100 kilometers. Once you're done, you switch the rocket off, and they come down, almost in the same place they took off. Not quite, but essentially in the same place. With no horizontal velocity, you cannot go into orbit. So let's think about those orbits. The definition of an orbit is simply the path of an object. That might not be quite how we think of orbits, but the definition of an orbit is simply the path of an object which is affected by gravity. In other words, if you're pushing an object or pulling it or doing something to it, then strictly speaking, it's not moving in an orbit. But if it's moving only under the influence of gravity, regardless of what shape path that is, it is still called an orbit. So we're used to the idea of planets orbiting the sun and probably moons orbiting planets. That's something we're quite familiar with. Kepler figured out that the planets move in ellipses. Sometimes they're fairly close to circles, but generally they are ellipses as planets move around the sun. Kepler made the observations, and Newton figured out why from his universal law of gravitation that says if you've got a gravitating body pulling these objects into orbits, they will orbit in circles or ellipses. Strictly speaking, there'll be one of these four shapes, so-called conic sections. This is what Newton told us a few hundred years ago. A conic section, take a cone, slice it. Depending on how you slice it, you either get circles or ellipses, or two other shapes, a parabola or a hyperbola. Now, we're used to the idea of circles and ellipses because those are so-called closed shapes. They come back on each other, whereas the parabola and the hyperbola are open shapes. They don't reproduce. They're not periodic if you think of an object moving along those lines. So if we think of objects moving around the sun, the little yellow dot in the middle here, we can imagine objects moving in circles or ellipses or possibly a parabola or a hyperbola. And for those of you in the know, you may realize that these curves that describe the way objects move around a gravitating body like the sun, they're the same shapes that are used to make telescope mirrors. So we might have spherical mirrors. This is two-dimensional, but if we imagine they're three-dimensional, we might have spherical mirrors or ellipsoidal mirrors or parabolic mirrors. The reasons that they are the same shapes for orbits of the sun as well as the shapes of mirrors is ultimately because the underlying maths is the same, and when you solve the equations, you get the same shapes. So we're used to the idea that planets in the solar system follow the inner circles there, the inner orbits, the circles or the ellipses. If an object is coming from a great distance, let's imagine it comes from a huge distance like the Oort cloud and simply falls into the solar system, then it will trace out the shape indicated there in red, the parabola. And if an object doesn't fall into our solar system, but is thrown into our solar system, if it has some velocity as it enters our solar system, then it will follow the shape given by the outer curves there, the so-called hyperbole. So we know that if we see an object on a hyperbolic trajectory, we know that it can't have simply fallen towards the sun. It must have entered the solar system at some speed. And this happened in 2017. The object called this rock that didn't have any name, this unnamed rock came into our solar system in 2017, and we followed it over a matter of weeks. And either by plotting it and seeing what its shape is, you can determine it's a hyperbola, or you can simply make a note of how fast is it going as it's passing the sun. And when that was calculated, we realized this object is traveling faster than the escape velocity. In other words, it is going to escape our solar system. That tells us that if it's going fast enough to escape our solar system, it must have been moving at some speed when it came into our solar system. If that wasn't the case, it would never escape our solar system. So we can work out a lot about orbits, not just by plotting them out, but by calculating things like velocity and thinking about escape velocity. So given that we're talking about orbital mechanics, one thing that's rather important is that we understand how orbits work. So here is just a schematic of two hypothetical planets, a green planet and a red planet, orbiting the Sun. The green planet is closer to the Sun, so it feels a stronger gravitational force. And the only concept that I want you to understand this evening is if an object feels a greater gravitational force, it moves faster. That's it, okay? So the green planet is closer to the Sun, so it moves faster than the red planet, which is further than the Sun, feels a weaker gravitational force, and moves more slowly. So clearly the red planet takes longer to do one orbit than the green planet. It's not simply the case that the red planet has got further to go, that is indeed the case, but if you look at the animation one more time, you notice that the red planet is moving more slowly than the green, especially when they overtake. You can see the green is definitely moving faster, so the red planet is moving more slowly and it's got further to go, which is why the red year is much longer than the green year. But this fundamental idea, if the force of gravity is stronger, then objects move faster, that in essence is all you need to understand rocket science or orbital mechanics. And if we look at a particular example in this particular animation, very close to Earth, my laser pointer doesn't work on a TV, but very close to Earth, we have the space station and the Hubble Space Telescope going around in about 90 minutes. A little bit further out, we have the GPS satellites going round the Earth in about 12 hours. And if you come all the way to the outer circle, there we have the geostationary satellites that are taking 24 hours to circle around the Earth. So again, the further you are from the Earth, the weaker the pull of Earth, the gravitational pull, and hence the more slowly those objects move. So a geostationary satellite moves much more slowly than, for instance, the Hubble Space Telescope, which is only a few hundred kilometers above the surface of the Earth, which goes around the Earth in about 90 minutes or so. So it's very easy to believe that, well, surely if we understand how these things work and we've got computers, we can calculate pretty much anything in terms of lots of objects orbiting each other, like the moon orbiting the Earth and the Earth orbiting the sun. But it's rather embarrassing to have to admit that we can only actually solve equations correctly and absolutely when we've got two bodies involved. As soon as we have three bodies, like the moon goes around the Earth and the Earth goes around the sun, there are no analytic solutions. We can get computers to approximate the solution, but with three bodies, we can't actually do it properly. We have to rely on approximations. So if we look at three objects orbiting each other, it looks like, well, isn't that nice and neat, three ellipses? But let's let this simulation run a little bit longer, and then we realize, oh, well, they're not actually quite ellipses, and oh dear, it's actually a chaotic system. It didn't look it when we first watched it. Over short enough timescales, it might look like everything is nice and orderly, but after a little while, we realize the system is chaotic, and we do not know how to solve the problem. There are only a very restricted number of situations where we can write down the equations and solve them and say, this is the answer. For everything else, we have to do simulations and get computers to do approximations to how we think things move. If we're trying to work out how Voyager is flying through the solar system, we ignore the fact that the moon is going around the Earth. That doesn't matter as far as Voyager is concerned. We have to decide how we're going to approximate the problem and then solve for the particular system we're trying to deal with. So let's think about how we get a spacecraft from one orbit to another. For instance, we are living on the surface of the Earth is going around the sun. How do we get from the surface of the Earth to Mars, for instance? This has been done a number of different times, and here's a little animation to show how this was done a few years ago. The blue is the Earth, green is Mars, and the purple line is showing a spacecraft leaving Earth and arriving at Mars. Notice that when we leave Earth and when we arrive at Mars, they are on opposite sides of the solar system. Perhaps you also notice that as we're approaching Mars, Mars is actually going faster than we are. Perhaps I should just run that once again, just so we can see that. We leave Earth, we're heading towards Mars. So we have to go a little bit faster than Earth to start with. That puts us on an orbit which takes us out towards Mars. As we approach Mars, notice that we're slightly ahead of Mars. Mars is catching us up, which means Mars is going faster than the spacecraft at this point. But that's how we get from Earth to Mars. If we simplify it and just look down from above and just imagine that Earth orbit and Mars orbit are nice, neat circles centered on the Sun. They're not, but let's just make that approximation. Let's get rid of all that rubbish and just say that's Earth orbit, that's Mars orbit, and what we're going to do is to leave Earth when it's in that position and arrive at Mars when it's in that position. Notice they're on opposite sides of the solar system. This seems counterintuitive, but actually this is the easiest way of getting from Earth to Mars using the least fuel. And I remind you that this particular cartoon here is not to scale. So what we actually do is follow that blue ellipse. It's called the Hohmann transfer. You might have heard of this for fans of films like The Martian, for instance. They talked about how are we going to get a supply mission back up to the stranded astronaut. They talked about waiting for the next Hohmann transfer window. You have to wait until the Earth's in the right position and Mars is in the right position, and then you can fly that ellipse. It's an elliptical orbit around the Sun. Once you have got into that ellipse, how do you get into that ellipse? Well, you basically go a little bit faster than the Earth, so you have to fire your rocket engine to give you a certain delta V, a certain change in velocity. Doesn't actually matter what the acceleration is. What matters is by how much have you increased your velocity. In other words, you decide for a given rocket engine, how long do I have to fire that engine to increase my velocity to the point where I can go from I was on the green orbit and now I'm on the light blue orbit. And when you get to Mars, remember what we said in the last animation, when you arrive at Mars orbit, Mars is actually going faster than you are. So if you want to land on Mars, when you get there, you have to give another kick. You have to fire an engine again to accelerate you up to the Mars speed. So you might say, okay, that all seems fair enough. You have to, you have to give a delta V kick to start with to get into this blue orbit, and you need another delta V to catch up with Mars. When you look at this, you think, well, okay, that's fair enough. But if I get to Mars and then I decide to abort, surely all I have to do is not give myself that additional delta V kick there when I arrive at Mars, and I will simply follow the blue curve and I will continue on that ellipse. So that seems rather attractive. I can send my rocket to Mars, and if I decide not to land, I simply do nothing and the rocket comes back to Earth orbit, which is fine. Until you remember that Earth takes a year to go round the Sun, Mars takes a little less than 2 years to go round the Sun, and the blue ellipse, which is in between the two, is about 1.5 years. So if you do follow the blue curve, when you get back to Earth orbit, you'll be back at Earth orbit 1.5 years later. Where's the Earth going to be in 1.5 years? It will have gone round the Sun once and then another half orbit. The Earth will be on the wrong side of the Sun. So if you decide to go to Mars and come back as quickly as possible, Earth won't be there anymore. That is a real problem with getting to Mars. That's one of the reasons that exploring Mars is going to be so difficult. Basically, if you want to make sure it's safe, well, you can't simply abort and come home. You have to plan for about 8 months or so to get there. You have to plan to stay on Mars for a while and then plan for another 8 or 9 months to get home again. In other words, it's going to take a couple of years or so. You always have to wait until Earth and Mars are in the right relative position in order to get you there as efficiently as possible. What about other planets, the outer planets in particular? It was realized in the 1960s that there's a good way of doing this which minimizes the amount of fuel you want to use. If you want to explore Jupiter and Saturn and Uranus and Neptune and Pluto, well, yes, you can do that by building the largest rocket ever, or you can be very clever and say, well, actually, we can use a gravity assist, a slingshot maneuver, if you prefer. We can actually use the gravity of the planets to help send us further out into the solar system. We can rob a planet of some of its energy, some of its momentum, and use that to slingshot us faster into the outer solar system. That means we don't have to fire our engines to go even faster if we want to explore the outer solar system. If we don't have to carry fuel to fire the engines, that means our spacecraft can have more scientific equipment, more cameras, more instruments, because we don't have to carry as much fuel. So A, it gives you a speed increase, which means you get there faster, and you can send more scientific equipment to explore or image the outer planet. So it's a win-win scenario to use a gravity assist. But how do gravity assists work? It's all very well for me to say, well, all you do is rob the planet of some of its angular momentum or some of its momentum. But if you think about falling into a gravity well, in other words, falling towards Jupiter and then coming away from Jupiter afterwards, you can liken that to a situation where you've got a ball on a mountain rolling into a valley. As the ball rolls into the valley, it gains speed. As it loses height, it gains speed. And as it goes through the valley, that's where it has the maximum speed. Fair enough. But when it comes out the other side, let's assume there's no air resistance, let's assume there's no friction, which a lot of physicists tend to do. Once it comes out the other side, it'll roll up the hill, and if there's another mountain on the other side of the same height, it'll end up back up there. What physics tells us, by a particular principle called the conservation of energy, whenever you lose a certain amount of height, you gain a bit of speed and vice versa. Well, that means that at any particular height, I can draw that horizontal line anywhere I like. The speed on the way in will be the same as the speed on the way out. In other words, I'll gain speed as I go downhill, but I'll lose it all on the other side when I go back up to the same height. And perhaps somewhat surprisingly, it makes no difference what the shape of the hill is. It can be very steep on one side and very shallow on the other, doesn't matter. At the same height, you will end up at the same speed. So that would sort of imply that you're never going to gain anything. Whatever you gain falling towards Jupiter, you're going to lose as you pull away from Jupiter. So how can Jupiter possibly give you an assist and make you go faster? Well, here's why. Let's imagine that we are doing a slingshot past Jupiter. So the maximum speed will be when we're closest to Jupiter. That will be the maximum flyby speed. And we can imagine we're coming in at some speed or another, and we're going out at some speed or another. And I've just said the inbound or inward speed at a given distance will be the same as the outbound speed at a given distance. So we don't win anything. Here's the clever bit. This is as seen by Jupiter. As far as Jupiter is concerned, the object coming in and the object going out, those two speeds will be the same. But Jupiter itself is moving around the Sun. And so, if your inward speed is, for instance, broadside, coming in one way, and your outbound speed is in the same direction of Jupiter, then Jupiter says this object is moving at the same speed, but Jupiter itself is moving, which means the object ends up getting an assist. And the difference can be as large as, for instance, it might be an object comes in at 10 kilometers a second and leaves the influence of Jupiter at substantially more than that, perhaps even 25 kilometers per second. So there can be an enormous speed bump as long as you get the geometry right. You've got to make sure that under ideal conditions, you leave Jupiter's influence in the same direction that Jupiter is traveling. And then you effectively have your velocity on top of Jupiter's velocity. And you're using the fact that Jupiter is going around the Sun to give you the assist. This was figured out by basically rocket scientists, if you want to call them that, orbital mechanics people, that figured out this is a way of getting an assist for effectively nothing. You simply have to make sure the geometry is right. And this was used back in the 1970s. Pioneer 10, for instance, left Earth, and then it went past Jupiter. See what happens when it passes the green dot? Bam! It suddenly changes direction and changes speed. Notice that it's now flying off at a much higher speed, and there's a complete dogleg in the direction. It came in broadside to Jupiter, and it left approximately in the same direction that Jupiter is traveling. We can see the same thing with Pioneer 11, which happened a little bit later. After leaving Earth, it went past Jupiter, got a gravity assist. Look at that change. It went in a completely different direction after it passed Jupiter. and it was flung on towards Saturn. Notice also that Jupiter and Saturn are on opposite sides of the solar system. It was still worth doing because you can do it for free. It takes a little bit of time to cross the solar system, but it costs you no fuel to use Jupiter's gravity assist to send you on to Saturn. And then Pioneer 11 also had another gravity assist from Saturn as well. The same things happened with Voyager in the latter part of the 1970s. Voyager 1, its prime mission was to image Jupiter and some of its moons as it flew past Jupiter, and then fly towards Saturn and get as close as possible to Titan, because Titan is a really interesting satellite with a very dense atmosphere. So there again, the gravity assist, the dogleg, and the sudden jump in speed from Jupiter, and fly on to Saturn. No gravity assist from Saturn, because Voyager 1's job was to fly past Titan, and if you're flying past Titan, that constrains where you have to be and when you have to be there, so they couldn't have any additional gravity assist. The tick marks, by the way, these vertical lines, just indicate whether the path we're looking at is either in the ecliptic, in the plane of Earth's orbit, or above or below the ecliptic. Voyager 1 was successful in getting close to Titan and taking images of Titan. So Voyager 1 satisfied its mission criteria, which means Voyager 2 was then able, instead of going to Titan, which has already been done, the idea was for Voyager 2, gravity assist from Jupiter, and then another gravity assist from Saturn, and that will send you on to Uranus, another gravity assist, and send you on to Neptune. Perhaps you noticed no gravity assist from Neptune. When they arrived at Neptune, they were already going fast enough to leave the solar system. There's no need to go any faster. And they wanted to have a close look at Triton, the main moon of Neptune, so they flew over Neptune's pole, and that's why this thing tends to dive down and go south of the ecliptic. So they went over the north pole of Neptune in order to get a good view of Triton. But the gravity assists meant that you could look at Jupiter, Saturn, Uranus, and Neptune with one mission without effectively adding any more fuel. You simply had to make sure your cameras and other instruments would last long enough for the years that it would take to reach the outer solar system. We can get an idea of what that looks like if we plot out the velocity. Here we're plotting out Voyager 2, Voyager 2, the speed as a function of how far it is from the Sun. AU, astronomical unit, in other words, in multiples of the distance from the Earth to the Sun. When we look at the velocity, we find very obvious results of the gravity assist. The speed falls as it comes away from the Sun, then you get a huge kick from Jupiter, and then it falls again as you move further from the Sun, then you get a kick from Saturn, and then it falls again as you head for Uranus, and then it gets another kick. Notice that although it gets a kick by falling into Neptune and its velocity increases, note what happens after it leaves Neptune. It ends up going more slowly than when it came in. So in other words, the kick is downwards rather than upwards. Remember, it went over the pole rather than getting a gravity assist to send it out faster. It didn't need to go fast because it was already going plenty fast to leave the solar system. There's the escape velocity from the solar system, the blue line. Notice that as you head towards Jupiter, a spacecraft, generally speaking, that we send towards Jupiter is not going fast enough to leave the solar system. But as soon as you get a gravity assist from Jupiter, that red line goes higher than the blue line. It's now going fast enough to leave the solar system. And the red line stays above the blue line, regardless of what gravity assist you get thereafter. So all of Pioneer 10, 11, Voyager 1, Voyager 2, they've all had gravity assists from Jupiter, and it doesn't matter what comes next. They will all be leaving the solar system. What is a little bit counterintuitive, I think everybody can appreciate that there's good reason to want to have a gravity assist to visit the outer solar system. But what's not so widely appreciated is gravity assists are actually quite handy for the inner solar system as well. For instance, Bepi Colombo heading towards Mercury. And it's done that not by simply diving towards Mercury and then going into orbit. If it tried that by falling towards the Sun, it would be going way too fast to go into Mercury orbit. So what they actually did was use gravity assists from some other planets like Earth and Venus, for instance, and then Mercury itself, not to accelerate, but to slow down. A gravity assist can either accelerate you or decelerate you. Either way, you save fuel, and that's the main advantage, that you can change your velocity either to increase your speed or to lose speed if you're falling into the inner solar system. But in both cases, the advantage is you don't need to use fuel to fire your rocket engines to speed you up or slow you down. So Bepi Colombo, this particular title you see here, Bepi Colombo 2018 to 2025, although it's not that far to Mercury, it takes quite a few years because you've got to pass the Earth, pass Venus again, pass Mercury, a number of different times to slow down a bit, slow down a bit more, slow down a bit more. There was a slight problem with Bepi Colombo. They're now reckoning that it won't go into orbit around Mercury this year, which was the original intention, 2025. It now looks like it's not going to go into orbit around Mercury until next year, 2026. They had a little bit of a problem with one of their thrusters. This is just a reminder that sometimes you do need to burn rocket fuel. You can't always use gravity assists. For instance, Cassini here, over its lifetime from 2004 to 2017, went through a number of different orbit changes as it went around Saturn. You can see a very complex system of orbits. Every time you change from one orbit to another, you're going to need to fire your rocket engine to take you from this orbit to that orbit. Why did they keep changing the orbits? Because they were studying Saturn. They were studying its moons. Hundreds of moons. They were studying Saturn's rings, and they wanted to keep seeing the planet or the rings or the moons from different angles to try and get as much data as possible. Eventually, in 2017, Cassini was crashed into the planet deliberately to make sure it didn't contaminate any of its moons. But if you're going to do that sort of mission, you have to make sure your spacecraft has got enough fuel on board to make your orbital changes for whatever mission that you have in mind. So let me move on to one of the most enigmatic ideas in orbital mechanics, and that is there are places in the solar system where you can park a spacecraft and it will just sit there. Not intuitive by any imagination, but I would argue the concepts are still relatively simple. Let me remind you, because this is the important bit, let me remind you how things move. And I'll say it again. The green planet is closer to the sun, so the green planet moves faster. The red planet is further from the sun, so the red planet moves more slowly and takes longer to go around the sun. That's how things normally work. And this is just a little cartoon reminding us that the pull towards the sun of the green planet is the red planet is a little bit less than the pull towards the sun of the green planet. So the green planet has got a slightly larger arrow. Greater distance, the force is less. And the question we can ask ourselves is that always the case? Well, for an isolated object, very remote from all other objects, that is the case. The further you are from the sun, the weaker the pull of the sun, and the slower the object will move. We can't change the gravitational influence of the sun, but we can arrange it, for instance, so that the gravitational force felt by an object in the red orbit feels an additional gravitational force. And this is where Lagrange points come in. Let's imagine that these aren't two planets. Let's imagine that the green object here is the Earth, and the red object is some object or another. Let's say it's a spacecraft. Let's imagine that the red dot is a spacecraft and the green dot is the planet Earth. If Earth goes around the sun in 1 year, then we would expect an object as in the red orbit would take longer than 1 year to go around the sun. But what if the red object was close enough to the Earth that it's feeling the pull not only of the sun, but feeling the pull of the sun and the Earth in concert? That means, remember, when the gravitational pull is stronger, the object moves faster. So instead of taking more than a year to go around the sun, with the extra pull, because the Earth is also pulling in that direction as well as the sun, the extra gravity means that instead of taking longer than a year, the red object is now going to take 1 year to go around the sun. So what does the pattern look like now? They both go around the sun in 1 year. They go around in concert. In other words, they do that. The length of time it takes the red object to go around the sun is the same as the length of time it takes the green object to go around the sun. And notice that the green and the yellow arrows showing the direction in which the gravitational pull on the red object is. Let me run the animation one more time. The red object is always feeling the pull in the same direction. It always sees the Earth and the Sun in the same direction. They are always adding together their gravitational pulls. And that will keep the red object always in that position. So it's moving, but it's always in the same position relative to the Earth. That's effectively what we mean by a parking space. So this idea of how objects move, that is precisely what we mean by, in this case, this particular Lagrange point is called Lagrange point 2, and it's sitting there at some distance from Earth, such that a spacecraft sitting at L2, Lagrange 2, will be pulled towards the Earth and pulled towards the Sun in such a way that it will take 1 year to go around the Sun, just like the Earth does. Now, this is quite definitely not to scale, because the distance from the Earth to the Sun is 1 astronomical unit, and the distance from L2 to the Earth is substantially less than that. It's only about 1% of an astronomical unit. Of course, if I tried to do it to scale, this particular cartoon would be a little bit messy. So I've just exaggerated the scales here. Again, a reminder, quite definitely not to scale. And for other Lagrange points, for instance, Lagrange point 1, that is inside the orbit of the Earth, but it's exactly the same principle. Now the Sun is pulling in one direction and the Earth is pulling in the opposite direction, because L1 is immediately between the Earth and the Sun. And so the gravitational pull on L1 is reduced because the Earth is pulling in the opposite direction. So without the pull of the Earth, you would expect a spacecraft at L1 to simply go round in less than a year, like Venus and Mercury do. But because of the reduced gravitational pull, because Earth is pulling in the opposite direction, instead of going round the Sun in less than a year, now an object at L1 goes round the Sun in 1 year. And so stays in that same position. If you park it between the Earth and the Sun, it will stay between the Earth and the Sun. Again, the cartoon is not to scale. Earth to Sun is 1 astronomical unit, and the distance to L1 is almost the same as the distance to L2. It's about 1% of an astronomical unit. Not quite the same, but it's very similar. L1, that particular location, because it's always between the Earth and the Sun, that's a very good place to put, for instance, a spacecraft to study the Sun. The Earth never gets in the way. The Earth and the Moon around the Earth never get in the way of a spacecraft sitting at L1. It has an uninterrupted view of the Sun, and yet it's always at that particular distance from Earth. How do we calculate where these Lagrange points are? Well, we can basically use Newtonian mechanics. There's nothing to do with Einstein and general relativity here. It's good old Newton. Newton said the force between two objects depends on the mass of those objects and the distance between them squared. That's it, effectively. So if we use the fact that the gravitational pull falls off as 1 over the distance squared, then we can calculate how far it is from Earth to L1 and L2. It's very simple. All we have to do is to solve that equation. And we can solve that equation for r, which gives us the distance to L1, L2. Simples. Okay, yes, I know. I did say at the start of the lecture that it's not that hard if you just skip the maths. Okay, so let's skip the maths. The point is, it can be done. It is basically just 1 over r squared, how the force falls off with distance, does allow you, okay, you need a little bit of maths to actually work out the numbers and find that the distance to L1 or the distance to L2 turns out to be about 1 million miles or so. But the concept is just what I've been describing to you. Strong gravity, faster motion; weaker gravity, slower motion. Yes, the maths gets a little bit messy and it starts getting a little difficult to see what's going on, but the concepts are just there. So back in the 18th century, Euler and Lagrange, a couple of mathematicians, a Swiss mathematician Euler and Italian mathematician Lagrange, worked out by pencil and paper that there are 5 places, these 5 dots you can see here, the 5 red dots. There are places where if you were to put an object there, in the ideal sense, ignore the rest of the solar system, if you place an object at any of these 5 points, the object will simply stay there under the influence of the gravity of Earth and the gravity of the Sun. L2 is where we've decided to put a number of different spacecraft. L4, L5, L3, perhaps not so useful. L3 is on the other side of the sun, so we can never see it from Earth. We could never communicate with any spacecraft that was sitting there. L4 and L5, well, there are reasons that you might want to go there, but L1 for solar observations and L2 turn out to be the most useful Lagrange points. And L2 is currently the home for a number of different spacecraft. It has hosted a number of spacecraft in the past and will host even more in the future. There are plans to put even more spacecraft at L2. If you take a spacecraft and sit it there at L2, you are sitting 1 million miles above midnight. Remember, the left-hand side of the Earth as we see it here is noon because that's facing the sun. The right-hand side of the Earth as we see it here is the midnight side of the Earth. So L2 is basically a point in space sitting 1 million miles above midnight. And that is where you can place a spacecraft with a suitable sun shield, as indicated by the little cartoon Gaia here, or the James Webb Space Telescope. A sun shield pointing towards the sun will also shield you from the Earth and will also shield you from the moon. So if you've got an infrared telescope, for instance, you can block all of the heat from the sun and the Earth and the moon with one heat shield pointing in one direction. L2, the actual point itself, is in Earth's shadow. You can imagine there the Earth will cast a shadow because of the sun shining on the daylight side of the Earth on the left, and it will cast a shadow. Earth is about 4 times bigger than the moon, so its shadow is about 4 times longer. The moon's shadow is long enough to reach from the Earth to the moon, about 250,000 miles. We're talking about 4 times longer, but Earth is 4 times bigger. So as it happens, Earth's shadow goes about to L2. So if you were to put a spacecraft at L2, you would effectively see an annular eclipse because the Earth would be blocking the sun. Not a great place if you are using solar panels to try and charge your batteries for your spacecraft. Also, it's not a good idea to put a spacecraft there because if you're trying to communicate with Earth, you've got a big radio transmitter, the sun, right behind it. So it's more sensible not to sit at L2, but to make an orbit around L2. That takes you away from L2 so you can see the sun, and it means that the Earth and the sun are in slightly different parts of the sky, makes it a little easier to communicate. It also means you don't have a road crash of all of these spacecraft all jostling for position at L2. You can put them in orbits and they can all agree with each other how they orbit around the L2 point. So what happens if you were to sit at L2? If you imagine what would happen if you were sitting at L2 at the red dot and you happen to drift a little bit in this diagram up or down, in other words towards the top of the screen or towards the bottom of the screen. Well, the Earth's gravity would simply pull you back again. In other words, if you moved a little bit up towards the top of the screen, Earth's gravity would gently pull you back down again. If you move towards the bottom of the screen, Earth's gravity would pull you back again. So it's a self-correcting system in that direction. However, if you drift in the other way, if you drift towards the Earth, you will continue drifting towards the Earth. If you drift away from the Earth, you will continue drifting away from the Earth. In other words, when we think about what's going on around that particular L2 point, it is not simply a gravitational well in which, doesn't matter which way you move it, you will always end coming back to the same point. We can visualize this, and this is how it's being done by mathematicians and physicists. Imagine that we have this particular surface. Imagine that this is a donut, which is basically looking at height above, doesn't matter, height above sea level, for instance, and imagine that we've got a little ball bearing that's rolling around on top of this donut. So red contours here represent high points and blue contours represent low points. Imagine what would happen to a ball at various points in this donut. That gives us an idea of how things would move in the vicinity of a Lagrange point. So let's have a look a little more closely about what's going on at L2. So I'm going to truncate it at L1. I'm just going to look at the Earth and L2, blow that up a little bit. Remember, red contours are high, blue contours are low. Where's a ball bearing going to roll? If you think about what's going on around the red dot there, if the red dot represents the L2 point, if the ball bearing is a little bit high, in other words, towards the top of the screen, it'll roll towards the red dot. If the ball bearing is a little bit low, in other words, towards the bottom of the screen, it'll roll towards the red dot. But what happens if it goes left or right, in other words, towards the right-hand side of the screen or towards the left-hand side of the screen? As soon as it goes away from that point, it rolls off the hill. And when we see that the two arrows are pointing in different directions, we realize that this particular point, L2, is not simply a hilltop. In other words, if it was a hilltop, it would roll off in any direction and would be lost completely. And it's not a well. If it was a well, you could move it away from the bottom and it would always find its own bottom of the well, regardless of which way you were moving. So this is neither a hilltop nor is it a well. It's what's called a saddle point. Mathematically, that would be described by a surface like that, where you can see why it's called a saddle point, because it's got the shape of a saddle. If you imagine a point right in the middle of the saddle, if you go in one direction, you go up, and there's a tendency to come back down to the middle of the valley. But if you go in the other direction, orthogonal to that, at right angles to that, you fall off the saddle. So L2 is actually a saddle point. So that's one take-home message from this particular talk this evening. The James Webb Space Telescope is sitting on a Pringle. Genuine Pringles have got this correct curvature. One way is one curvature, the other way is another curvature. Certain supermarkets sell false Pringles which don't have quite the same shape, but the genuine article is saddle-shaped, and that is what the James Webb Space Telescope is sitting on. So it is possible to park objects like Gaia or James Webb, and they do little orbits. I say little, they're actually quite large, but in principle they're small orbits around L2, and you don't have to worry about burning a lot of fuel to stay in orbit because the Earth is keeping you in orbit. All you have to worry about is that very slowly, as time goes by, you will occasionally drift towards Earth. And if you drift towards Earth, you basically let it go for a few months, and maybe after 6 months you say, well, it's drifted enough, let's fire the old thrusters and push us back to where we want to be. And then we wait another 6 months and we drift very slowly towards the Earth, fire the thrusters, put it back to where it needs to be. What you have to make sure is you don't go too far. If you go beyond L2, you haven't got any thrusters to bring you back again, because then the thrusters would be on the telescope side, not on the sun shield side. Remember, the sun shield is pointing at the sun. That's where all the hot stuff is, on that side of the sun shield. The telescope itself is cold because it's an infrared telescope. And there were no thrusters there. If you fired thrusters on that side, any exhaust from the thrusters would condense on the James Webb mirror and you would ruin your telescope. So it's only got thrusters on one side, so they deliberately keep it just this side of L2 to allow it to drift towards the Earth and then station keep, and then drift and station keep, being very, very careful not to push it so far that it goes beyond L2. Let me finish with some very odd bits of celestial mechanics, or at least orbital mechanics. Some orbits are really, really weird. For instance, with a shape like this, a donut like this, you can trace the contours and say, well, in principle, an object could follow one of these contours. For instance, it is possible that an object follows an orbit like that, which looks totally and utterly ridiculous. The arrows say which way the object is actually moving. But actually, if you bother to actually have a look at it very carefully, it still obeys the rules. The rule is when gravity is stronger, you go faster. When gravity is weaker, you go slower. And if you follow the arrows, you can imagine it getting pulled towards the Earth. And when it's a little bit closer to the sun, its gravitational pull to the sun is stronger, which means it goes round, not in a year, it goes round in less than a year. In other words, it follows the arrow because it's going round faster than the Earth is going round the sun. Remember, this is a static picture, but the Earth is always in motion around the sun. And when this object is further away from the sun than the Earth, its gravitational pull to the sun is weaker, which means it takes longer than a year to go round the sun, which means the Earth seems to catch it up because it's going relatively slowly and the Earth is taking a year to go round the sun. So although it looks really, really, really weird, it's still obeying the rules. Stronger gravitational pull, faster motion. Weaker gravitational pull, slower motion. And that's not just purely hypothetical. There are objects in the solar system which follow horseshoe orbits. Some really weird moons of Saturn, one of the moons of Uranus. Whether or not you call it a moon, because it's actually in an orbit, which is the same as the Uranus orbit, but instead of actually going around the planet, it follows this horseshoe shape. So if you're interested, you can look up Crantor. It's a small rocky body which follows a horseshoe orbit, and there are a number of other shepherd moons which follow very odd orbits as well. So, as I've just said, it does obey the rules. When closer to the sun, it goes faster. When further than the sun, it goes slower. The concept is simple. It's only the maths that gets in the way of trying to map out what that actual shape is. And perhaps the weirdest orbits of all, we're used to the idea that orbits are circles or ellipses or something else, but they don't have to be closed shapes. For instance, what if you start with three objects, red, green and blue indicated here? If I place them there and then just let them go, what's going to happen? Well, blue is going to be attracted to red and green, so it's going to go down the screen, presumably. Red is going to be attracted to the other two, so it's going to go to the right. Green is going to be attracted to the other two, so it goes to the left. But trying to predict what they're actually going to do, unless you actually do a simulation, it is very surprising to find out what actually happens. Nobody would have thought that that's what they're going to do. And then they will slowly stop under gravity, and then gravity will pull them all the way back again, and they will follow exactly the same trajectories back again and follow exactly the same lines. They are not circles, they are not ellipses, they are not closed orbits, but they're still orbits. They are the motions of particles influenced only by gravity. And don't get me started on black holes, because as soon as you start thinking about black holes, space and time are so distorted around a black hole that you can't possibly start talking about circles and ellipses or anything else, because all bets are off. You have to then throw away Newton and start asking Einstein, how is this thing going to behave? So let me summarize. Why is rocket science considered to be so hard? Why do people say, that's not difficult, it's not rocket science is really hard, everything else is easy? Well, yes, it is certainly true that there are some objects in the solar system which move in ways which are counterintuitive. Nobody would have figured out a horseshoe orbit was possible until you sit down and figure it all out, and then you find, okay, simply by obeying Newton's laws of motion and Newton's universal gravitation, gravitational pull makes things go faster, etc., then you can figure out that horseshoe orbits exist. But by no means is it obvious. You have to sit and figure it out. And yes, I would admit that putting the James Webb Space Telescope at the L2 point, in orbit around L2, with such exquisite precision that they got it there using such a minimal amount of fuel that they've now kept enough fuel for it to station keep, not just for 5 years or 10 years, but perhaps they've got enough fuel to station keep by giving it a nudge every few months for maybe the next 20 years. That is a credit to the people who figured out how do we get this object to orbit that point in space which we think exists. There's nothing there, but we think this L2 point exists. Let's send our spacecraft there and orbit, and it should do exactly what the mathematics tells us will happen. The underlying ideas I've been trying to emphasize this evening are really, really simple. Stronger gravitational pull leads to faster motion. In other words, Earth goes round the sun faster than Mars goes round the sun. That's it. Everything else is just maths. And let's face it, it's not rocket science. Thank you very much.